receptors have high noise and low spatial resolution and contrast resolution. Okay, not so much contrast resolution anymore. Our contrast resolution is not really controlled by our image receptor, but our computer algorithm. All right, so that's one. Number two, high spatial resolution and contrast resolution require low noise and slow image receptors. Again, not so much anymore. Slow image receptors was a thing, but really, right now, we're not using slow image receptors. We're using high-speed image receptors. 400-speed image receptors or even higher. Low noise accompanies slower image receptors with high spatial resolution and contrast resolution. Okay, so the second half of that is still true. You know, we desire the high spatial resolution. It's a little bit lower than what it was with screens and films, but your eyes can't pick it up anyway, so does it really matter? Especially if we introduce such a high contrast resolution that you can bring out those structures and see them a whole lot better. And the answer is really fundamentally no. So our contrast resolution, superior contrast resolution, sacrifice a little spatial resolution. We're not using slow image receptors anymore. So we've kind of just walked through an awful lot of this. We're going to take a look at what the H&D curve is here in just a bit, if we have time, and how it applies now. So we used to have to chart our processor chemistry and how exhausted it was, and that was the foundation for the H&D curve. We don't do that anymore, but we still use it as a visual, and we'll talk about that here in a bit. So traditional screen speeds, I kind of talked about that. In the transition from, you know, slow to high speed and high speed to CR to CR to DR. So how screen speeds, how we manipulated screen speeds were we had inside of the screen, we had these things that were sensitive, there were phosphors that were sensitive to X radiation. So we make an exposure. Let's see if I can put it that you can see. So what happened with our screens is our films were light sensitive. Okay, so they're sensitive to all different kinds of light. Different manufacturers had safe light options. So Kodak, for example, worked off of a green spectrum. Well, what's green?
Green screen.
Green screen, yeah. But what is the color green? How do you get green? Blue and yellow, right? It's blue and yellow. So it was sensitive to blue and yellow light primarily. It wasn't sensitive to red light. So whenever you see in a movie somebody's processing, you know, films, you see in a movie that they're in a dark room and they're processing the films and they've got a red light. That's because their film is most sensitive to green and yellow light. So it's affected by phosphors, but it's also influenced by KVP. If you increase KVP or you increase mass, what you get then is an increase in the glow on the screens. So the higher, the more those screens glow, the more density you put on the image. Okay, so that's screen speed. Film speed is the same thing. The film speed primarily was affected not just by the chemistry in the screens, but the thickness of the chemistry. How much chemistry did you put on the film? So we kind of walked through this last semester in physics. What we did was we took the films and we put it inside the intensifying screens. The intensifying screens, the light in the intensifying screens is really what exposed the film. And then we took the film and we put emulsion on both sides of the film and used two intensifying screens, right? So all of that increased film speed. Sensitive to radiation and light, and they had to be spectrally matched. Okay, so we had two basic types of films. Kodak made one, and I forget who made the other one. But Kodak Kodak was, sensitive to red, sensitive to green light, you know, so the screens would glow green, and the film was sensitive to that green light. The other one was sensitive to, I want to say, primarily yellow light, and so they could use, blue light. So they could use either a yellow or an amber safe light, or they could use a red light, either one. Okay, so the point to all this is if you used a Kodak film inside of the other cassette, then it's going to be less efficient because it's only going to pick up those blue light waves, right? So they had to be spectrally matched, and what that means is the right film with the right screen so that you optimize the amount of light that you're going to visualize.
I recorded 3 videos in our lab that I wanted to show you, and these are exposures of open intensifying screens so that you can see what's going on inside of the screen whenever we make an X-ray exposure. So there's 2 different types of screens I mentioned in class. One was rare earth, and the other is the one I couldn't remember at the time, as calcium tungstate. So rare earth screens glow green, and that's what you're going to see here. Calcium tungstate glow solely blue. So the first one that I'm going to show you has an unknown mass value. It's a 1 second exposure, 70 kVp. So you get the exposure, you can see the green glow right there. It's kind of dim, so it's relatively low mass, moderate kVp, but we'll get some sort of glow. So what these did for us was the film was exposed more by the glowing of the light than what it was with the X-ray. So one X-ray photon that strikes the crystals, just a single crystal in here could release as many as 400 light photons, thereby intensifying the image, and that's why we call it a intensifying screen. So we could cut back on our radiation exposure by a factor of maybe 400. So it doesn't recognize kVp versus mass. So what I tried to do in this one was to use some semblance of the 15% rule, even though I didn't really know what my mass value was on this first image. I kind of played around with it to try to show you a brighter glow for a shorter time. So that would be something that we would want to use for like if we were doing pediatric patients. And this last one is for a higher kVp, a higher mass value, and the glow is really pretty bright on this one. You see it there. So playing it one more time. It's still short exposure, so it's kind of hard to stop on it. So that's what our intensifying screens were and are, and how we would use those in order to cut back radiation exposure to the patient. So,
And how dark the image is going to be. So sensitometry is a study of the effects of exposure